share application screen. I'm going to share with all of you, and you should be able to see it, what I'm going to share it, right? All right. So, and you tell me whether you can see it or not. Can you see the slide? Yes? Can you see the slide?
Yes,
Yeah,
we can see
Yes.
it.
thank you. Thank you very much. All right. So if you recall, basically what we have done so far, let me go to the larger screen a little bit. All right. So we have discussed several things before the first test, I guess, right? And that includes but not limited to organic compounds, electrolytes, non-electrolytes, the properties of the electrolytes, and application in our health. We also talked about the application of the osmosis of the solutions and osmolarity and how it is applied to our health again, right? So these are things we already talked about it. These two are done. The last part of the list about the solutions is the dialysis. Dialysis is the phenomenon. Basically, we dialyze. So if we have two solutions, one has some electrolytes, another doesn't have those electrolytes, then if we put it together somehow, then they will diffuse. That's called dialysis. Dialysis. By definition, it looks like this. So write it down, please, right? The separation of larger molecules, dissolved substances, or colloidal particles. Colloidal particles are the suspension, just like milk. Milk is one of the example of the colloids. Cheese is one of the example of colloids. Particles from smaller molecules, substances, or colloidal particles by a semi-permeable membrane. Again, the same thing comes up, right? Semi-permeable membrane. Remember, it was used for the osmosis. It has tiny holes. It allows some molecules to pass, some molecules are trapped. So the separation of larger molecules, dissolved substances, or colloidal particles from smaller molecules, substances, or colloidal particles by semi-permeable membrane. That's the definition, that's the process. So basically, if you have some component in one solution, another component, those components are missing in a second solution, if you put them together, the component from the first solution will diffuse to the second solution. That's basically it is. And I'll show you the application within a minute. So this is the image of the dialysis of protein solution, for example. Protein is the bigger particles, right? We have 75% protein in our body. Protein is a molecule, right? We eat protein, egg, right? So if you have a beaker, for example, like this, and you have the solution outside, and you have inside the protein solution. This protein solutions, what you have in there, and this is the dialysis bag. This is called dialysis bag, BAG, and it is a semi-permeable membrane. So it has certain molecules, like these are protein particles, the bigger ones, right? They are bigger ones, and smaller one, circle one, the greenish color, is the reagent or solvent, leavening solvent or so. And the molecules, the red color, they're there in the solution outside, they're not inside, right? So what will happen, they will go inside and this green one will come outside. That's basically it is, because exchange. So this is at the beginning and the end. What basically will happen, what will happen, you have those red dots, those are solvent particles, they're coming in, and the green dots, which are inside, they're coming out. So that's basically the exchange. And that's called dialysis. It's a dialysis.
Could you go back to the last slide for just a second?
Sure. Okay. So
Okay, you're good now.
all right. So this is the way it is done. It looks like a static, but usually it is not static. What basically is done, you put in a platform we call the magnet. So put a tiny magnet around here, a magnetic bar, a magnetic plate, and in the magnetic plate that can rotate. So you can control it with a motor. So this can rotate, right? As it's rotating. So this is rotating, for example, and inside you put a magnetic bar, a tiny magnet bar. So when this is magnetic bar inside the beaker on the bottom, and this is outside, that's a plate, and that basically spin it. So as you spin it, it's spinning. This magnet is also spinning, right? That's basically spin. So magnet is also spinning. As magnet is spinning, now the whole dialysis bag is spinning. whole dialysis bag is spinning. So that way, those molecules can come out faster. So basically spinning that, if you leave it like as it is, the diffusion process is very slow. Diffusion means coming out and getting in, right? They're very slow. But if you put a magnetic bar, then basically it helps. It helps. So basically after the same thing, you have the same thing this side too. I'm not writing it. So basically this by spinning it, and you have some air on the bag, that's why it will not sink and it will touch the magnetic bar. If it does touch, it might break because semi-permeable membranes are fragile, very, very fragile. So that's why this is called dialysis. And this is, someone can turn off the microphone, please. All right. So that's basically the dialysis with the magnetic bar and spinning, and therefore you can exchange some particles from inside the bag through the dialysis, through the semi-permeable membrane, and some particles can get in, as you can see from there, right? So what's the application of this? This is the general application, right? This is a general procedure, but it has a tremendous impact in our health. How? Our kidney, our kidney is the dialysis center. Our kidney in our body, right? All animals, all including human beings, they have a kidney, and kidney is a dialysis center. What it does, it has a cells called nephrons. Everybody hope you know that, right? The nephrons. So nephrons, basically, those are the tiny, tiny cells, and outside the cells of the nephrons has a semi-permeable membrane. Very, very tiny, tiny holes. So what does it do? What does it do? As you remember, what basically happens when we eat, our food goes to the stomach, digestion starts from the mouth. After the digestion, we get many, many molecules, glucose, nutrients, minerals, small peptides, hormones, lipids, fatty acids. They all go inside the cells. When they go inside the cells, they degrade, they metabolize, right? Called metabolic processes. Once they metabolize inside the cell, with the help of mitochondria, it generates many, many toxic chemicals. For example, it can generate carbon dioxide from the TCA cycle. We'll talk about down the road. It can generate some molecules like acetic acid, like from our pyruvate. It can also generate the urea, very toxic chemicals. Urea, everybody knows urea, right? Urea is good for the plants, but not good for the human or good for the animals, cells. So therefore, and also ammonia, NH3. So those, and uric acid, some other things, just name a few. So those molecules are toxic, generated from our metabolic processes. They have to get out, right? They have to get out from our body. And how? So basically, those toxic chemicals or molecules will basically dump into our blood. As it dump into our blood, then basically what happens, that blood will go inside the nephrons. All those nephrons. So this glomerulus, if they say glomerulus, nephrons. So these nephrons basically go inside, the blood is going inside those glomerulus and filtered, just exactly this exchange. What is exchanging? They're exchanging the bad chemicals with the good ones. So bad ones are coming out, good ones stays. Good ones means we have minerals, we have some sugars, we need those, right? So whatever we need, body needs, they'll stay. The toxic chemicals will come out. As they're coming out through all those processes like that, ultimately they'll come to the collecting duct, and that's basically the bladder there, urine bladder, and it comes to the urine. So it will come right there. So basically, if you in expanded version, if you see from here, these numerous things, so they're coming through this blood. Every drop of blood, every RBC must go through there. And as they're going through, the waste product, the urine, it goes to the bladder, and those waste product goes to the bladder. That comes to urine, and ultimately it goes to the outside, right? That's basically our filter process. So kidney is the dialysis center. Now, if someone has a problem, as you probably know, some people do have some problem, the kidney problem, and that's called kidney failure. If the kidney doesn't work very well, the patient. Yes.
I have a question. Okay, so the blood goes into, like, I think you said the nephron, and then when it goes out after it's been cleaned or whatever, does it go out back into the body, but like the toxins go through the collecting?
Absolutely. You will see it within a minute. I mean, so this is the enlarged version of the glomerulus nephron. and then it goes to the body. Yes, it goes in, comes out, and goes back to the lungs, heart, and all those things. Absolutely. So some people do suffer from kidney problem, right? And as they do, that's called kidney failure. They can live. They have to go to the dialysis center. So what happened in the dialysis center? So this is basically the dialysis chamber that you can see from there. So patient with the kidney failure needs artificial dialysis at the dialysis center for survival, right? So if you can see from there, so dialysis in, so that's basically a solution. The dialysis going through the circle. So blood gets in, blood is coming in, going through the process outside, and it's filtering. The bad chemicals are coming out, and as they're coming out, they basically ultimately all the way it goes out. And then the blood comes out to the other end and goes inside the body again. So that's the hollow chamber. That's a semi-permeable membrane there. And if you see the real setup, it goes like this way. So as you can see from there, no offense, right? It's kind of any space could be any patients. So this is the cylinder, as you can see from right there. And these are the machines they're operating it. So what you have in the machine, as you can see from there, so that's the blood. Now the blood pump in, it going through those to the chamber, filtering out, and goes back to the go to there. So it's coming from the, as you can see from the, this is our, let's assume this is our artery. So it's coming through the artery, goes all the way, filtering out. Remember, those toxic chemicals must be removed and going to the vein. And the only thing, as you know, the nurses, the expert nurses, they can identify which one to get in, which one to get out. Right? It's very, very important. As you know that the getting in, the arteries are pumping the blood, so that's basically pumping it, and the veins are getting in, right? They basically goes to lungs. So that's the clean blood goes to the lungs, and then it oxygenated, and ultimately it goes to the heart, goes to the cells. And as you're doing it, ultimately you can see the drops of urine. It looks like urine color too, anyway. But anyway, so that's basically the waste products are coming from there. And it takes about, depending on the individual, it takes about 4 to 6 hours, and it's once in a while, once a week or so, something like that, depending on the progressive of the disease, how the kidney is working or not. So that's basically the application of the dialysis. All right. Do you have any questions? I'm done for on the first part, the ionic compounds, their applications. I wish I could finish this one before the test, but apparently I'm running a little late. But it's okay; it's not that bad. So that's basically. And for the next test, definitely a question or two will be from the dialysis. So you must remember this. And whatever I told you, I'll ask the question in a way that you understood what the procedure, what it does, and what are the chemicals it basically filters out. And if they're not done or filtered out from the body, what are the consequences? All right. So now I'm moving to the next phase. Question.
Can you go back to the last slide really quickly?
Okay.
Thank you.
You do not have to draw the picture, but I should just understand that. Understanding is good enough. Okay. All right. So let's go to the next page. The next page. Remember, when we talk about the ionic compounds, we had many polyatomic anions, and I told you at the time that they came from one of the polyatomic cation came from the base ammonia, and rest of them came from the acids or bases. Acids or bases, right? Only one polyatomic anion, OH minus hydroxide ion, came from the bases, and the rest of them, sulfate, phosphate, nitrate, nitrite, sulfide, hydrogen carbonate, etc., all of them came from the acids. So we'll go to the acids and bases now. It's okay? All right. So that's basically the origin of the polyatomic anions, and more is acids and bases, as we told you earlier. All right. So we are talking about the acids and bases. All right. So what are the acids? Origin of acids. The origin of acids are coming from this. Non-metal oxides, non-metals. Can someone name me what is the non-metals? Can someone name one at least? Yeah.
Hydrogen.
Sure. Yeah. Okay. But let's go. Hydrogen group 1. Go from 5, 6, 7. Right. So hydrogen, or let's say carbon. Come on.
Oxygen.
Oxygen. Nitrogen, all we are adding the oxygen, that's fine. Nitrogen, sulfur, phosphorus, etc. That's fine, right? Good enough. We'll come back to those. There are many of them there. So non-metals bind to the oxygen, make a non-metal oxides. And you saw that, right? You saw that. I'll show you more. Non-metal oxides, when react to the water, they make acids. So what's the origin of acids? Origin of acids are the non-metals. Non-metal react to the oxygen and make non-metal oxides. As you probably remember, many of all who do not know, but our evolution says what basically happened, it is happening all the time. So let's say carbon, nitrogen, oxygen, sulfur, phosphorus, when they go to the top of the earth, right, in the stratosphere region, and oxygen is there, and with the electric current, they can combine, they can metal oxides. And then when it rains, it makes acids. And as you probably know, Amazon River, Amazon area, the tropical area, the rains all the time. And they do all those things. And in the rain, if you analyze, there were plenty of acids. And if the acid concentration is too high, it is called acid rain. Acid rain, because it's coming from the coming with the rain, right? And that's why also you know that rainwater is very good for the plants because they bring acids. Acid dissolves the metals, and those minerals they can get it. So the bottom line is the origin of acids is the non-metals. I'll give you some plenty of examples. Next slide is examples. It's okay? All right. So carbon plus oxygen make the carbon dioxide. It's not balanced. All right. Just I'm writing the compound alone. Sorry. So carbon dioxide. Carbon dioxide gas, G for gas, H2O, L for liquid, make the H2CO3, carbonic acid. Remember the carbonic acid, right? And that's a carbonate right there, CO3. We'll come back to that one very soon. Likewise, nitrogen, or it is balanced anyway, I will balance it for you. So nitrogen gas plus oxygen make a N2O5. This is called nitrogen pentoxide. Nitrogen pentoxide. Nitrogen makes another compound too. So if you have a nitrogen, for example, let's say G, I'm writing another oxide, G plus O2, I'm not balancing it here. And you can also have N2O3. Can someone tell me what's the name of this? What's the name of this molecule? Does anyone know? So you have N2O5, you have N2O3. Does anyone know? This is a nitrous oxide. Remember arsenic, higher valent, lower valent. You have a higher number of oxygen right here, lower number of oxygen there. So nitrous acid oxide, nitrous oxide. If you take the nitrous oxide and if you take the H2O, you get this molecule. H2O, you get HNO2. HNO2. Remember NO2 minus nitrite ion? That's the nitrous acid. Nitrous acid. So nitrogen plus oxygen make two oxides. It make many, but two of them are important in terms of the acids. Nitrogen gas plus oxygen, not balanced here. You get the N2O3, nitrous oxide. Nitrous oxide dissolves in water, make the nitrous acid. Nitrous. Everything okay? Right? Nitrous. Nitrous. TROUS. Nitrous acid. Nitrous acid. Us, right? Remember us? If you have a nitrogen pentoxide, 5-oxide, pentoxide, dinitrogen pentoxide or nitrogen pentoxide, reacts to the water and it makes the HNO3, nitric acid. That gives the nitrate ion, NO3 minus. We'll come back to those again. So nitric acid, the origin of nitric acid is the nitrogen. Origin of nitrous acid is the nitrogen. Origin of carbonic acid is the carbon. Let's go to phosphorus. So phosphorus plus oxygen make the P2O5, phosphorus pentoxide. Phosphorus pentoxide. Likewise nitrogen, the group 5 elements. So phosphorus pentoxide plus water, it makes the not balance here. I try to balance some, but not all. Okay. You have a H3PO4, phosphoric acid. Phosphoric acid. You know the phosphoric acid, right? And the phosphate ion, PO4 3 minus. We'll come back to that again. So phosphoric acid. So the origin of phosphoric acid is a phosphorus. Makes the oxide, dissolves in water, make the phosphoric acid. Everybody knows the AQ means, right? AQ is the aqueous. All right. Sulfur plus oxygen. Sulfur can make sulfur trioxide, SO3, and SO3 dissolves in water, make the H2SO4, sulfuric acid. There is another sulfur. Sulfur can also make another compound. It is called S plus O2. All right, S plus O2, very similar to nitrogen. You get the SO2, sulfur dioxide, right? 2 sulfur dioxide. If you add the water to it, H2O, it's a gas. Sulfur dioxide is a gas. H2O liquid, and you get HSO3. Now, who can tell me what's the name of this? H2SO3. H2SO4 sulfuric acid. H2SO3. What's the name of the H2SO3? Someone? Yeah? Sulfuric acid, sulfurous, like nitrous, sulfurous acid. And the polyatomic anion comes with the SO3 minus. We'll come back to that, right? For example, chlorine. Chlorine can react with oxygen. Chlorine can react with oxygen and make the dichlorine heptoxide, Cl2O7. All 7 electrons are used to make oxide. Cl2O7 plus water, it makes the HClO3, perchloric acid, very strong acid. Sulfuric acid is very strong acid. Nitric acid is very strong acid. Perchloric acid is very strong acid. Strong. Weak acid could be strong and weak, right? Depending on the electrolyte, strong electrolyte, weak electrolyte, based on the dissociation, but similar. So nitric acid, strong acid. Sulfuric acid, strong acid. Perchloric acid, strong acid. Carbonic acid, weak acid. Phosphoric acid, weak acid. All right. So these are the acids. I just give you some, and you can also have a perchloric acid, perbromic acid, periodic acid, perfluoric acid. Not good, not much known, but that's okay. So halogens can make also these acids. Now, these acids, they contain oxygen, right? All contain oxygen. So acids with oxygen. Halogens can also make acids too. So halogenic acids. H2 gas plus X2, X would be fluorine, chlorine, bromine, iodine. It can make 2HX, or X is a fluorine, chlorine, bromine, iodine. These are halogenic acid, and you have seen it, right? Hydrofluoric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid. Now, who can tell me, how do you see the hydrochloric acid? We have plenty of it in our body. Or is it? Anyone? Why do you see the hydrochloric acid inside our body? Yeah?
In our stomachs?
Our stomach. Yeah, plenty of it. The pH is a very high concentration HCl. That is correct. This digests our food. Oh, sorry, excuse me. So these are the acids. So acids with oxygen and halogenic acids. Any question about the acids? It will be the test anyway, one way or another. Most of the origins and yes. All right. Okay. So yes.
How did you know that it was a weak acid or a strong acid?
I'll come back to that. Very good point. That was the next step. We'll come back. So let's go to the origin of acids, right? Then we'll classify strong, weak. I just mentioned you briefly. I'll come back to that one so that you can see it again. And then we'll go to the origin of bases. All right. So origin of bases is as follows: metals, group 1A, 2A, 3A, to some extent transition metals. Metals plus oxygen make metal oxides, and we have seen it, right? N2, Li2O, N2O, K2O, etc., right? MgO, magnesium oxide. You know the metals, right? Everyone knows the metals, right? So you have a sodium, group 1, calcium, right? Ca, calcium, group 2, aluminum, group 3, all the metals, right? And the others are there too. Sodium, potassium, rubidium, lithium, calcium, magnesium, strontium, barium, aluminum, gallium, indium, those are all metals, right? They will make the compound with metal oxides. These metal oxides, when react with the water, they make bases, alkali. It's called alkali. Remember the group 1 metals called alkali metals? This is the name came from, alkali, because that's where the first discovered. But other group A, group 2A, and group 3 elements also make the same kind of things. All right. So let me, the metal oxides, or they're also known as metal hydroxide, MOH, or depending on the group 1 or group 2. Examples are as follows. These are examples. So group 1A elements, sodium plus oxygen, make the N2O. You have seen it, right? You can also get the same kind of things. You can get the K2O, right? Potassium oxide. You can get the lithium oxide, Li2O, right? Exactly the same way. Because the group 1 elements, right? Metal oxide, group 1 metal oxide, for example, sodium oxide. These are solid, by the way. Solid, S for solid, G for gas, L for liquid. Adds the water, H2O, and becomes sodium hydroxide, aqueous solution. Sodium hydroxide, NaOH. Remember, right? So, likewise, if you take the lithium oxide, dissolve in water, you get the lithium hydroxide. If you take the potassium oxide, dissolve in water, you get the potassium hydroxide. Same thing, rubidium oxide, rubidium hydroxide, cesium hydroxide, etc., could be generated following the same reaction, following the same reactions. So the group 1 elements, bases react with oxygen, make the, sorry, metals react with oxygen, make the metal oxide that dissolves in water to make the metal hydroxide. Metal hydroxide. Group 2 element, magnesium plus oxygen, magnesium oxide. And similarly, we can do the calcium oxide, right? We can get the calcium oxide. We can get a strontium oxide. Very similar, exactly the same, because they are group 2A. Likewise, barium oxide, BaO. We can get all of those oxides. Very similar kind of formula, right? Magnesium oxide, calcium oxide, strontium oxide, barium oxide, exactly the same way. Now, if we dissolve that group 2 metal oxides plus water, you get the magnesium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide, and as you probably remember, these hydroxides are insoluble, right? Remember the solubility rules? So these are basically insoluble, the solids. That's basically what I'm saying. But barium hydroxide is aqueous. Note, because barium hydroxide is strong base. We'll come back to that. Someone asked the question, very good point. So sodium hydroxide, all group 1 elements, hydroxides are strong bases. Group 2 elements, they're insoluble. The group 2 element hydroxides are insoluble mostly. Barium hydroxide is the exception. It is a soluble and very strong base. We'll come back to that, right? So everybody okay, right? How the group 1 elements makes the hydroxide, group 2 elements make the hydroxide, group 3 elements, aluminum with oxygen make the L2O3, not balance, okay? L2O3, aluminum oxides. You can also make the same thing, sorry. You can make the same thing. You can make a gallium, Ga2O3, gallium oxide. You can make the indium oxide, In2O3. These are all group 3 elements oxide, right? Now, if we take the group 3 elements oxide, dissolve in water, you get the hydroxides, group 3 element hydroxide. Aluminum oxide plus water, aluminum hydroxide, solid, aluminum hydroxide. Likewise, you can make the gallium hydroxide solid, indium hydroxide solid, etc. Could we make the same following reactions? Okay? So group 1 elements, group 2 elements, group 3 elements. React with oxygen, make the respective oxides. Those oxides, when dissolved in water, they make respective hydroxide. Remember, all have a OH, right? That's the signature motif for the bases. You saw the previously, the acids all have a hydrogen. So signature motif of the acids is proton, H+. We'll come back very soon. Any questions? So the origin of the bases is the metals. Question?
Could you go back a slide real quick, please?
Okay. It's all right. Yes.
Thank you.
You're welcome. Any other questions? All right. If not, let's go to the next one. So the definition of acids. How to define an acid? Here comes the question that someone asked you, how do you know strong acid, weak acid, okay? The first one defined in 1860s. The name is the name of the scientist called Arrhenius. Arrhenius. So Arrhenius' definition of acids is as follows. Acids dissociate in water to generate H plus proton that binds the water, make the hydronium ion. Hydronium ion. Hydronium ion. Measured by the pH, which is the negative log of concentration of hydronium ion. Everybody knows the water, right? So water is HOH, right? That's or OHH, H2O, plus if you take the proton, H plus proton coming from the acid. Remember, oxygen has a lone pair, two pairs of lone pair, right? I'm just writing like this. One pair of lone pair will give it to the hydrogen, H plus proton. And as it gives the proton that H plus, you'll have a O oxygen, H, and H. This H just made a new bond, and that and one lone pair remains as it is. So since it given the lone pair, two electrons are given to the hydrogen, that positive is transferred to oxygen. And that's the structure of H3O positive. This is known as hydronium. Hydronium, hydro is water, nium ion attached to the proton. Water attached to the proton called hydronium ion. So that's the structure. So remember, whatever writing there you must write, because if I ask the question, the structure of hydronium ion, I'll phrase it in a way exactly what is written right here. And as you know, whatever I say, I ask the question. I'm not going to ask any other things. Whatever I discuss, you are responsible. I am responsible, right? So therefore, you must know. If I ask the structure of hydronium ion, this is the structure of hydronium ion. So it could be phrased in a way that you know this. Otherwise, you cannot answer the question. So remember, all right? Very good. So once again, acid dissociates in water to generate hydronium ion. And how do you measure the hydronium ion concentration? It is measured by the negative log of concentration. Parenthesis indicate concentration. That's a log, natural log, base 10. I didn't write the 10. So negative log of concentration of hydronium ion is called pH by definition. By definition. And I'll come back to how to measure the pH or all sorts of stuff. We'll talk about this. So if I ask the question, I ask the question different way, a little bit complex way, of course. What's the pH? Calculate the pH of this solution. So you must know what is the pH. pH is the measurement of the concentration of hydronium ion in a solution. What is the hydronium ion? It's a complex of H proton and water, and that looks like this. Looks like this. All right. So these are the signature modes. So all acids have a H plus proton. That's called signature motif of proton of the acids is proton. It's proton H plus. We'll talk about signature motif for bases is OH minus. We'll come back, right? So now let's take some acids. Let's some examples of acids, how the acid works. So let's say nitric acid plus H2O. It will dissociate into nitrate ion. Remember the nitrate ion? NO3 minus plus hydronium ion. Let's say perchloric acid. They are strong acids plus H2O, perchlorate, ClO4 minus plus hydronium ion. So how many hydronium ion generated from here, from these two acids? One, right? One proton, one H, one hydronium ion. This is called monoprotic. Protic stands for proton. So monoprotic, meaning it has one proton, monoprotic acid. So nitric acid, perchloric acid, monoprotic acid. There are many. I will give you some example. Nitrous acid is also monoprotic acid, but two examples is good enough for the timing, right? That's called hydronium ion. So number of hydronium ion generated from the after dissociation is a monoprotic. It depends on the monoprotic or diprotic. So let's go to the diprotic. Sulfuric acid, H2SO4. H2SO4. Add water, you get H2SO4, 2 minus sulfate ion, right? 2 hydronium ion, 2 H3O positive, because there are 2 protons there. 2 protons there. And one arrow indicates the complete dissociation. So these are complete dissociation, this is a complete dissociation. You can take another diprotic acid, Carbonic acid, H2CO3. Water, you get the carbonate and 2 hydronium ion. And this arrow indicates, I cannot write the reversible, I can, but this one indicates basically it looks like this, goes like this and goes like this. So reversible. Reversible means, what's the reversible means? It has this component, those are called products. You also have some remaining undissociated stuff. That's weak. That's a signature of a weak dissociation. Nitric acid, perchloric acid, they dissociate completely, near 100%. Sulfuric acid dissociate completely. It's almost a diprotic acid, and it is also strong acid. So strong nitric acid, perchloric acid, sulfuric acid, they dissociate completely. So strong acids. Carbonic acid dissociate reversibly, weakly, partial dissociation. It's called weak acid. And how to determine what percent, we'll come back later on, right? And so you can see the sulfate ion, carbonate ion, and why these two acids are called diprotic? Because they're making 2 hydronium ions. 2 hydronium ions. Okay. Similarly, you can go to the triprotic acid. The triprotic acid, one such example, not too many are there. One such example is phosphoric acid, H3PO4. Add with the water, it will dissociate phosphate ion and 3 hydronium ion. 3 hydronium ion. So it's making 3 means 3 proton, triprotic. 2 protons, diprotic. 1 proton, monoprotic. Mono is 1, right? So mono, di, triprotics. All right, and it is also is a reversible. I just put it in that way. It's a reversible, meaning it has some phosphate on there, some hydronium on there, and some undissociated phosphoric acid is also there too. That means it is dissociating partially, incomplete dissociation. That means weak acid. Weak acid. So carbonic acid, weak acid, phosphoric acid, weak acid, nitric acid, perchloric acid, sulfuric acid, they are strong acids. So someone asked the question, remember? So how we define how do you know? Basically, we look at the dissociation. We look at the dissociation. And how do we look at the dissociation? Basically, look at the concentration of the hydronium ion. So when you have let's say 1 mole, 0.1 mole of this, and you get a 0.1 mole of that, and that will be measured with a pH. There is a pH meter machine there that can tell, yes, complete dissociation. And if you have a carbonic acid, for example, and if you see the concentration of this, it is not that this hydronium ion concentration doesn't correspond exactly to the concentration of carbonic acid. Less, always less, meaning it's a partial dissociation. And once again, how do you measure the concentration of hydronium ion? By the pH, with the pH meter. There's some solution there. There's some way. All right, so that's basically the dissociation. So monoprotic, diprotic, and triprotic. So if I ask you a question in the test, and I will, right? So you can ask like this way: the sulfur, when it reacts to the oxygen, it makes this. When that compound added to water, it makes this. Is that compound a monoprotic acid, diprotic acid, or triprotic acid? Did you get the question? Nitrogen react with oxygen, make a compound. That compound dissolves in water, make an acid. Is that acid? Make another compound. Is that compound monobasic, monoprotic, dibasic, diprotic, tribasic, or triprotic acid? I can ask many different ways. Did you get it right? All right. So now let's go to the next one. So this is RNA's definition. Now we got the basis. Right?
I have another question. So with that question you were asking us about the test. So is there like certain atoms that are always like monoprotic? Like is nitrogen always a monoprotic acid?
Mostly. Chlorine, bromine, iodine, they also make a monoprotic acid too. Yes, sure.
And then so is sulfate always diprotic?
Always sulfur diprotic, yeah.
Okay, thank you.
I mean, sulfur makes diprotic acid, yeah. It's origin of, yes, sure, yeah. Shall I go on, move on? Yeah. All right, so let's go to the RNA's definition of bases, alkali. So bases dissociate in water to generate hydroxide ion, and everybody knows the OH minus, right? We talked about one of the polyatomic ions, OH minus, measured by the pOH, very similar to pH. What's the pOH? Is a negative log of concentration of hydroxide ion. Negative log of concentration of hydroxide ion. So basically, you can you can calculate the pOH from the machine, and the machine is only designed for the pH, and there is a relationship between pH and pOH. I'll come back. So if you know the pOH or pH of a solution, you can also calculate the pOH of a solution as well. I'll show you very soon. Everybody okay? So the bases are measured by the bases dissociated in water to generate hydroxide ion. The concentration of hydroxide ion is determined by pOH, and what's the pOH? Is a negative log of concentration of hydroxide ions. Similar to the acids, we can also have a monobasic, dibasic, and tribasic, depending on how many hydroxide ions they're generating in water. So let's say sodium hydroxide. I put a liquid, but it's a solid. It's usually solid, but if you have solution, that's a different story. So you can say aqueous or S, solid. If you add some water, you get the sodium plus and OH minus. Remember, that's the ionic compounds. And you know the structure of aqueous, sodium plus, OH minus. Potassium hydroxide, H2O, and making the potassium plus hydroxide ion. These are basically one arrow I'm basically indicating is equal sign because it's complete dissociation. So that's a strong basis then, right? And this sodium hydroxide, potassium hydroxide, lithium hydroxide, which I did not write, right? Lithium hydroxide, rubidium hydroxide, cesium hydroxide, they're all are group 1 elements that also make they generate 1. So lithium makes 1 plus. I did not write the aqueous, right? It's the same thing, OH minus. So they are generating 1 OH minus. That's like a monobasic. Mono means 1, basic. Similarly, if you have a barium hydroxide, dissociate completely, right? Equal sign. Calcium hydroxide, dissociate partially. The group 2 elements. Strontium hydroxide, magnesium hydroxide, they're all basically they dissociate partially. And you can get barium plus 2 plus, calcium 2 plus. If you have a magnesium 2 plus, strontium 2 plus 2 OH minus, all cases, 2. So they are generating 1 molecule of base, generating 2 molecules of OH minus, right? That's called diprotic. Same thing, triprotic, generating 3, and that's a group 3 elements. Aluminum hydroxide, gallium hydroxide, indium hydroxide, added to water, they'll dissociate partially, right? The 2-headed arrow, I just put it like this from the computer generation. It's a partial dissociation. It's when it can have ions as well as undissociated compounds there too. So you have aluminum ion plus 3 hydroxide ion. So monobasics are generating 1 hydroxide ion. Dibasics are 2 hydroxide ion. Tribasics are generating 3 hydroxide ion. So tribasic. And the concentration, once again, the dissociation is measured by the pOH of the solution. So you need to take some amount of the compound, dissolve in water, and see what's the pOH of the solution. That will tell you whether it is complete dissociation or partial dissociation. If it's a partial dissociation, if the strong dissociation, 100% dissociation, the concentration of OH minus and concentration of sodium hydroxide in the solution are equal. That's an equal sign. If it is a partial dissociation, concentration of hydroxide ion is not equal, always less than the concentration of the calcium hydroxide or the weak base dissolved in water. So everybody okay, right? So how to define the bases? How to define the strong bases versus weak bases? Now, from this, who can tell me is the magnesium hydroxide is a weak base or strong base? Magnesium hydroxide is a strong base or weak base?
Would it be strong?
Magnesium hydroxide.
isn't it a group 2, which is dibasic? So couldn't it go either way?
It can go either way. I mean, it's weak. It's weak. It's a partial dissociation. Remember, all hydroxides are insoluble. They're partially soluble also. They dissociate partially. So group 2A, group 3A, all hydroxides are weak bases. Exception is the barium hydroxide. Is the only exception that dissociate completely.
So the only reason, that monobasic bases are able to dissociate completely is because they're paired with group 1A elements, which always dissociate in water. Okay.
Yep. Remember our solubility? That's basically coming from the solubility. Yeah, you're right. All right. Now, here's a question I asked in the test. A metal, a group 2A metal, let's say magnesium. I just give you the name probably. Magnesium reacts with oxygen to make a compound. That compound dissolves in water to make another compound. Is the resulting compound, the last compound, is a monobasic, dibasic, or tribasic? What is it?
Dibasic.
Thank you. Indium, element indium was oxidized to make a compound. And ... The name of the compound, you have to give the date and name of the compound. That compound, when dissolves in water, make another compound, ... resulting compounds. Is the resulting compound monobasic, dibasic, tribasic, or triprotic?
Tribasic.
Thank you. Thank you very much. Excellent. Very good. All right. So remember, this kind of things question will be asked in the test. Okay. Or sorry. Definitely get ready for those, right? And then I'll come back to the pH and pH. Those are the lots of questions will be asked from this test. Okay. All right. So that's our dissociation. Now, the strength of acids and bases. So that's a summary. Acids.
It's 11:50.
How much time we have?
It's 11:50.
Time's up.
Yeah, thank you for letting me know. I don't have a watch here. I should have a watch here. I'm going to put some watch somewhere. It's happening right every day. Okay, I'll see you Friday. Okay, see you Friday. Okay, get ready. Whatever I talked about, whatever I said, the questions, and questions will be asked anyway, one way or another. So work on it. Okay, and get ready. And I'll ask some questions in the beginning of Friday's talk. Okay. Sorry.
Yes. I do have a question for you.
Yes, I'm here. So let me